All right. Welcome, everyone. We're very pleased to have Paul Han from Northeastern University, who will give a presentation today. Paul did his PhD at NYU. After that, he did a postdoc at MIT. And then he moved on to Rice University in the Department of Computational and Applied Mathematics. And then he moved on again, and he's now assistant professor in the Department of Mathematics and Computer Sciences at Northeastern University in Boston. His research interest is in theory and algorithms for machine learning and AI in the context of vision and imaging. I got to know Paul's work through his very interesting earlier work with on phaseless recovery. So I'm sure that he'll touch on that subject here as well. So Paul, the stage is yours. Go ahead.
All right, thank you so much for the invitation to speak, and thank you for organizing this wonderful series. I know I've enjoyed many of the presentations myself, throughout COVID. I want to spend some time, sharing some of the ideas I've been thinking about related to solving inverse problems using tools from machine learning. And these tools will be something called generative models, and they can be used as priors. So we call this generative priors. So just as a recap, just to set the stage, I know this this audience is quite familiar with these sorts of problems. But we have, and we're studying inverse problems, and so for the sake of this talk, we will talk about primarily linear inverse problems, but also some nonlinear inverse problems. So for example, we'll talk about denoising, inpainting, and super resolution, where you have some linear operator phi of x naught for some x naught, some image x naught that you want to recover. And that operator phi could be something that adds noise. It could be something that only subsamples some of the pixels, or it could be like provides a low resolution version of the image. We'll also talk a bit about compressed sensing and phase retrieval. And so phase retrieval is the problem where phi is, say, the absolute value of linear measurements of your signal x naught. Right. So these are the sorts of problems that we'll talk about. They have many applications. For example, like compressed sensing can be used for magnetic resonance imaging. And here, this is a very significant, societally important application where, like, really trying to get high quality images from relatively few measurements can demonstrably impact people's lives, and that being in an MRI machine could be quite harrowing for many people because it's a very small space. And so if you can accelerate the MRI, then you could get diagnoses much faster, you could increase the efficiency of these machines, etc. So what you see on the screen now is an image of an MRI, sort of visualization of data that could be collected from that MRI, where here this shows Fourier space measurements, but you'll notice it has this vertical banded structure. That's because the device is not actually measuring everywhere in Fourier space, it's only measuring along these vertical lines. And there's a compressed sensing problem of figuring out, what does the image look like, even though you have fewer measurements than you should. There are a whole bunch of other inverse problems that are interesting, seismic imaging, which is pictured on this top left. On the bottom left is, the cocktail party problem, where lots of people speaking in a room and a microphone or a series of microphones might pick up the superposition of the speech of multiple people in this room, and your goal is to try to disentangle this. Also electron microscopy. So as we know, there are many, many interesting types of inverse problems, and we're looking for categories of tools to help solve these problems. So the outline of this talk, I want to focus primarily on compressive phase retrieval. So I want to actually begin by talking about some classical methods, particularly sparsity, and its failure so far at solving the compressive phase retrieval problem. Then that's going to lead into sort of the main meat of the presentation today, which will be about deep learning-based generative models. And so using these tools, one can train low dimensional priors. And then there's some interesting things that we can prove and can demonstrate empirically about the efficacy of these low-dimensional priors for solving compressive phase retrieval. And then the last bit of the talk today, I'll talk about something called normalizing flow models, where we step away from low-dimensional deep learning priors to high-dimensional deep learning priors. And then this allows for some quite surprising, like, out-of-distribution results. All right, so this is the outline for the presentation today. So let's start at the now classical techniques, right? So the main one that I want to initially talk about is the idea of sparsity. And so sort of famously, we're probably quite familiar with this idea that say you have an image such as this boat in the top left, you can take a transform, like a wavelet transform, and then you can truncate the coefficients of that signal that are relatively low. You can reconstruct the image, and here in this image, they do this in the bottom right, and then with relatively few wavelet coefficients, you can get a relatively high fidelity reconstruction of this image. Right? So this comes back to the idea that natural images are approximately sparse in particular bases, such as the wavelet basis or like the discrete cosine transform and various other bases. Right, so this leads to a method for solving inverse problems. Right, you want to enforce a prior. You have some observations. Here, these observations, maybe we'll call this forward model of X. So there's some image X, you're observing the forward model of X. And so then those are baked into these observations. And so what you want to do perhaps is to minimize over sparse X of the sum norm of the observations minus your forward model of some signal X, which you're optimizing over. Right, so this, this is a quite famously successful, method for solving inverse problems. When we look at this method now, the thing that we can't help but notice is that this is what we would call like a handcrafted image model, right? So what this means is that, like, humans, like, we made a description of this image class, right? We're saying like this class is sparse in a wavelet basis, like, like people built wavelets. Right? And so they were built using a variety of principles, and they were shown to be effective both empirically and theoretically. But these are, but there's sort of room for improvement because one could, for example, have used machine learning. One could have actually learned a way to represent these natural images as opposed to sort of like imposing it from this like handcrafted model. So mathematically, this view of images being sparse in a particular basis happened to be coupled with a very convenient relaxation, which allowed for the resulting optimization problems to be efficiently solved. Right, so sparsity can be optimized via convex relaxation. Under this view of an image as being sparse in a particular basis, then we would naturally write down a optimization problem like what's on the left. So here, this is minimizing the L0 norm of some signal X, subject to the measurements that you've taken of X should be the measurements that you observed for a particular, for some unknown signal X naught. Right? And this famous L1 relaxation of this problem has allowed us to solve, in many cases, this sparse recovery problem using techniques of L1 optimization and linear programming. And then this culminated into this now famous theory from Candace Romberg and Tao and from David Donahoe. And I want to sort of put this theory on the screen now because it's going to be a guiding template for some of the work that I'm going to describe in a few minutes about generative priors. Right, so just to remind ourselves of what this result was. Right, so here we're in this framework of considering an image X naught to be modeled as sparse in a particular basis. Without loss of generality right now, let's let that be the standard basis. So let's fix a K sparse vector X naught. And our goal is to recover X naught from as few linear measurements as possible. So let's tuck those linear measurements in a matrix A So here we have m linear measurements of an n-dimensional vector. And so then we're going to write down this L1 minimization problem like from the previous slide. We want to minimize the L1 norm of x subject to the measurements on x agreeing with our data. So subject to ax equal ax naught. And then, so the result here is that with only k log n over k measurements, you can successfully recover any x naught with high probability. Right? So this is sort of like, in a sense, the gold standard result that we like want to replicate in other areas. Right? So it's a very clear, like a recovery guarantee using a computationally efficient method that's acting at optimal sample complexity. So this sample complexity is optimal because, well, there are k coefficients that are non-zero. Even if you knew which k those were, you would need k measurements to pin them down. All right. So this is the background. This is the standard classical tool which we're seeking to try to do a bit better than when we can. Right. So despite all of the successes of compressed sensing, and there are quite many theoretical and empirical successes in it, there has been sort of a persistent challenge, and that is that there are certain nonlinear inverse problems where sparsity doesn't appear to work. And so one such problem is compressive phase retrieval. So in this problem, we have, so this is very similar to the compressed sensing problem, but we, instead of having the measurements of ax naught, we actually have measurements absolute value of ax naught, either in a real valued or a complex valued sense. Right, so here there is some signal x naught. There are measurements absolute value of some matrix acting on x naught equals b, and given a and b, you're trying to find x naught. Right, so here we have m nonlinear measurements of x naught instead of m linear measurements. And the challenge here is that there's no known efficient algorithm for recovering, say, a S sparse signal x naught from O of S generic measurements. So now when I say generic, I mean, for example, that those measurements are this, for random Gaussians. If you're able to design your measurements to like bake some structure into them, then there are solutions that operate at optimal sample complexity for compressive phase retrieval under non-generic measurements. But for generic measurements, there is no known method now, and there may never be, since there are some reasons to believe this may indeed be computationally hard. For example, from some work from Bertet and Rigolet, showing that like the sparse PCA problem can be reduced from the planted clique conjecture, which is believed to be false. So it may be that the idea of modeling images as sparse simply might not work for certain nonlinear inverse problems. I mean, there are other perspectives which highlight the difficulty here. There are a whole variety of methods for solving phase retrieval. For example, there are like convex relaxation, such as phase lift, which was introduced by Vlad Voroninski and Thomas Stromer, Emmanuel Candez, and Yonina Eldar. And there are natural ways of extending that sort of convex program into handling sparsity, right? So the standard way of handling sparsity, like as we saw, was to put an L1 penalization on a term. So one could write down this semi-definite program, which is called phase lift, add this L1 norm of x term. So what I mean by that is like the basically vectorize x and treat it as literally the L1 norm of that vectorized x, just the sum of the absolute values of the entries of the matrix x. And so it's very natural to write down a problem like this. But back in 2012, Xiaodong Li and Vlad Voroninski proved that basically this method can't work, right? That if this method were to work, then you would need S squared measurements in order to recover an S sparse signal. And when we look at this here, right, this method of solving the problem was to take a vectorial quantity, search for a matrix recovery problem where the vector you're looking for is really the rank 1 component of this matrix. And so that is to say, it took an S-dimensional signal and then an S sparse signal, and then took the outer product of it with itself. So now you have an S squared sparse signal. So it's no great surprise that you can only do that you can only get away with a number of measurements proportional to S squared. Right. So this is sort of a pessimistic result. This combined with the Bertet and Rigolet paper may lead us to believe that like modeling compressive phase retrieval using sparsity is a bit of a direction that might not bear fruit. So we can think about like, why is this? Like, is there something left on the table using a sparsity model? And what I want to comment on is that I think there is. And we can phrase this by saying that like sparsity is not a tight prior, right? So here, what you're seeing on the left is an image of a shark. And then you could take the wavelet transform of this image, you can permute the coefficients, you can reconstruct it, and what you get on the right is not a natural image, right? So certainly we know that images have structure. There are relationships between the coefficients in a Fourier, in a wavelet expansion, that co-occur together. But nonetheless, like this fundamental model of describing something as sparse, like it really leaves something on the table unless we're going to go way out of our way to then model the dependencies of all of the wavelet coefficients. And indeed, there are works that do this in like model-based compressive sensing. Right. So there's slack that's there that we could maybe pick up on and capitalize on. Right. So now I want to bring in the deep learning, bring in the generative modeling, and how we can use them to get low dimensional priors, and what we can say theoretically and show empirically about those low dimensional priors, particularly for compressive phase retrieval. Right. So let's start. Here's an article from the New York Times in 2018, right? How an AI cat and mouse game generates believable fake photos. And here, researchers at NVIDIA trained something called a generative model, which is a neural network, which can take random noise and then convert it into like high resolution, photorealistic images of natural people. Here's another example of entirely artificial person generated by this model. And the comment here is that these are synthetically generated yet realistic looking images. And so this opens up the possibility of using these sorts of tools for inverse problems, right? Because if you're looking for an image that's consistent with data, right, we're looking for natural images that are consistent with data. Now we have a synthetic way of describing what is natural, that can be learned from existing data. Right, so that existing data looks something like this. These are images from a data set of celebrities. And so then you can train a model to generate synthetic new faces by having that model study or learn from a distribution such as the one that is behind the images that you see on the screen right now. And of course, there's nothing particularly special about faces. Any data class that you could have a lot of examples from, then you can train a generative model for. So faces, there's also common data sets of bedrooms, but you can imagine also for MRI scans, cells, images of cells, fingerprints, etc.
Paul, there's a question. I'm going to let Manny talk here. Manny, go ahead. Manny?
Oh, hi. Very enjoying your talk so far. Okay. I just have a question because your characterization, I'm not familiar with phase retrieval, but your characterization of sparsity doesn't seem to be maybe it's intentional. It's the modern sparsity do use a group concept of group sparsity and structure sparsity, right? It's no longer the original Candace Donahue in which And when you consider group sparsity and structure sparsity, that is really a much stronger prior. And I would argue it's actually very similar prior to why convolutional neural net can work, because convolutional operator is fundamentally exploiting kind of a soft shift invariance, but more important, local self-similarity. So I don't know. Maybe you actually are going in that direction. So I'm just asking this now. Yeah.
Yeah, I mean, I think there's definitely never going to be one true model to rule them all, right? Like that's, you know, like we're all familiar with enough science to know, you know, there's never one model, right? So some things when I consider a prior, like one of the things that I think about is, like, is it a linear prior or a nonlinear prior? And this is sort of, we'll see like a visualization of in a second, but a lot of models that describe subspaces or describe signals as belonging to the union of subspaces. That allows us to ask, do we really believe that the natural signal manifold is the union of subspaces? And those subspaces extend all the way out to infinity. And I, deep inside, I feel like, no, I don't believe that union of subspaces is really the morally right way of describing natural signal classes. Really, I view them as like nonlinear manifolds that are embedded in image space. And so now that leads to the challenge of, well, how do you actually find that nonlinear manifold? You know, it turns out that like this is something which like deep learning has happened to do a very good job at, sort of like uncovering that manifold from data. Certainly there are other tools that could do that too. But that's kind of when I look at sparsity-based methods, including like group sparsity-based methods, I sort of see the linearity in it and feel that any linear model is going to have is going to leave things is going to leave bits on the table, because there's a lot of images that are not natural that model will describe. So this you know, what I want to do is say something like this, very perhaps like perhaps a bit provocative, but hopefully like inspirational to think about us to question like, what priors should we really be using? And indeed, I mean, the generative modeling priors like have their challenges too. And we have a whole section of this talk dedicated to trying to like patch up some of the challenges introduced by this perspective. All right, so
because I work with generative models, okay. It's very interesting. But I think your constant focusing on prior is absolutely spot on. I'm just trying to suggest that we should not. I don't like. I'm concerned that we treat deep learning as a universal magic prior, and give up our ability or inclination to analyze what really the implicit prior that is encoded in a deep neural net. That I'm not sure if that makes sense, but I should let you go on. Sorry.
Yeah. I feel like, I mean, this is an interesting question. We can come back to it, and it gets to like some of the challenges of these new tools is that we don't understand them well enough. We don't really know where the regularization is coming from, and that's problematic. But that's you know, why we work in this area, to help to bring some understanding to them. All right, so then I will continue by telling us a bit, a bit about sort of the mathematics behind what's going on with these generative models. Like here, we should think of them as doing distribution learning. So I have a probability distribution. Let's call that pi naught. I have samples from pi naught, and I want to learn pi naught. And so when I say learn pi naught, I want to be able to generate new samples of it, maybe have a parameterization of those samples in a low dimensional way. All right, so then a tool for doing this is to build, a neural network. In this neural network that's shown on the screen, there might be a low dimensional input, so a low dimensional latent code to this neural network, And then the output of that network is like a high dimensional image. In a certain sense, you could think of that low dimensional code as like a compression of that image. And so then if you put in different random code Z, you're going to get different random images out on the outside. And these are all hopefully samples from the natural signal class you're interested in: faces, cells, brain scans, whatever. And so then this is our model. Right? So low dimensional input, neural network, gives you a high dimensional output. But in image space, you now have a low dimensional manifold, which is the range of such a generator. Right? So just to visualize, what this could look like. Let's say you have like data that's like in these left columns, like here's this 2 moons data set. Each data point, each blue dot or red dot on the left column, you should think of as like an image. And then on the right-hand side, there's some latent space. The dimension of these doesn't have to be the same. And then there's some mapping that goes from latent space to image. That was the function that I showed on the previous slide given by a neural network. And there's some process, perhaps the mapping, that goes from an image to the latent representation of that. And this is what a generative model is trying to do. You give me a random latent variable, I push forward through some function G, then I'm going to get a sample from this distribution, hopefully. All right, so how do you use this for inverse problems? Well, there's this this workflow, which is you train a generative model to output images of a certain signal class. So that generative model, like we just said, might take random noise as input and give you a random flower if you're studying a flower cast. And then given some measurement operator phi, then you might directly optimize over the range of the generative model by minimizing like L2 error. So minimize, say, over Z in RK. So K is the dimensionality of the prior, so that each image has a K dimensional representation. And so you want to find the Z such that G of Z equals X naught. That's the goal of the problem. You're assuming that the image that you're looking for is in the range of this learned function G. And so you then optimize over the error given the measurements you have. Right? So the prior here is that Z is in the range of G. And so if you have a good G, then Z will be close to that range. If you don't have a good G, then you're out of luck. All right, so this method was introduced and famously by this paper from Bora, Jalal, Price, and Demakis from UT Austin, right, where they looked at compressive sensing using generative models, and they showed that with an appropriately trained generative model, you could successfully recover images with like 5 to 10x fewer measurements than sparsity-based priors in certain regimes. And so they studied this formulation of just minimizing the L2 loss of A G of Z minus A X naught and doing this optimization. And they present empirical and theoretical results for this problem. So, but this talk really is about like compressive phase retrieval. And so I want to talk about this work that I did with Vlad Voroninski and my former graduate student Oscar Leong, who's going to be a postdoc at Caltech this fall. And this work is on using a generative model for compressive phase retrieval. So the formulation, while it took a little bit of tweaking to get right, the formulation is very similar to what the Bora paper did for compressed sensing. It's just that we have the nonlinear measurements from phase retrieval. So here we're optimizing over this low dimensional code Z. We're searching for the Z such that absolute value of AG of Z is close to our measurements absolute value of AX naught. Right? So we minimize the square norm of the difference between these. Right? So like let's see the picture of what's going on, because I think this like reveals it more clearly than the previous slides. Right? So we're in we're talking about images. So we're in some high dimensional image space. So you could imagine that there's some manifold of natural images, like all things that could be taken by a camera. And so that's what's given by this surface. Then there might be a sub-manifold of that, which is the actual like natural signal class that we're interested in. You know, maybe images of trains, or maybe MRI images, or whatever your particular application is. So that's this like red sub-manifold. And now we have linear measurements of a image. They are underdetermined because otherwise you would just solve the system. And so that's drawn by this dark, thick line. And so then there's hopefully going to be one point of intersection between that line and the natural signal class. So this is how how the prior is working, right? It's saying that you're on this low dimensional manifold. Oh. All right, and so I want to just sort of like jump like straight into the theorem that I proved. Again, this is with Oscar Leong and Vlad Voroninski. And so what we showed was that under a particular model for generative models, we have a recovery theorem for images that operates at optimal sample complexity using a computationally efficient algorithm. Right? So what is the optimal number of measurements? Well, in this case, that should be k, right? That's because the prior, so it had some latent code z, which was k dimensional. And so then your image was the push forward of that k dimensional z through this model. So that push forward of all the space will be a k dimensional manifold. So you really need k, you have k degrees of freedom that need to be specified. And you can't do any better than that. All right. So, all right. So we're assuming that we have k measurements up to log factors. Then we're going to make some assumptions on the particular neural network. So I know, like, I haven't spent time in this talk going into like the details of the architecture of this neural network, but for those of you that know, this will be for a like fully connected network without biases. And with RailU activations is the model that we studied in this paper. Right, so we're going to assume that each layer of this network is sufficiently expansive. So that means like the number of neurons or the width of each layer grows as you go deeper into the network. That is a somewhat realistic assumption because after all, this network takes this compressed latent code and then outputs this highly non-compressed image with a lot of redundancy. So roughly speaking, at each layer, you're adding complexity. Now, of course, with real generative models, you don't always need to have the layer width grow, and oftentimes you have several layers in a row that have the same width, but that's not described by the theory that we put forth. And so then the other assumptions that we're going to make is that our measurement model, our measurement operator has random entries. So this is back because we wanted to study the generic compressive sensing under generic measurements. And then we're also going to assume that the weights of the neural network itself are random. Now, this is the assumption that perhaps warrants the most pause, right? Because after all, the way neural networks are trained is you start with random weights, you give it some data, it learns stuff from the data, and so then those weights get modified, and so they're no longer strictly random anymore. And so nonetheless, like we're still going to assume that the weights of the generative model are samples from a random distribution. And some comments about this are like the post-training, there are cases where you can look at the statistics of the neural network's weights, and those often have statistics that are approximately Gaussian. There's also some existing theory out there that shows that in the cases where we can prove convergence of training of neural networks, often they're in a regime where the weights actually provably don't change very much from their initialization. And then the final justification for this assumption is that well, you got to start somewhere, right? Like at the end of the day, like I don't have a very good model for what the weights of a trained neural network is. Because to do that, I would need like a good mathematical model for like, what is a cat, right? What is a dog? Like mathematically, I don't know what those are, right? So basically out of mathematical necessity, in order to say anything, we need a model for the weights of the network, and so we're going to choose the entry-level model of initially random, and it can be refined from there. All right, so now what is the theorem? Right, so the theorem, and it's actually like evolved a little bit from what's stated on this slide, but the L2 sort of the non-convex objective that we wrote down on the other slide, this theorem states that under these assumptions, that objective has strict descent directions in latent space outside of two small neighborhoods, one around the global minimizer and one around a spurious negative multiple of it with high probability. And then sort of follow-up work, which is under review, proves that then you can take this and turn it into actually a gradient descent algorithm, and that gradient descent algorithm provably converges to the exact minimizer. And that work, is like I said, is currently under review, and it involves sort of just a little more detailed analysis of how gradient descent works in this case, and sort of some convexity-like properties around the global minimizer in order to guarantee global convergence. All right, but the bottom line here is, under this random model of a generative model, then we can do compressive phase retrieval at optimal sample complexity in K. So K, the dimensionality of the signal prior, right? And so this is in contrast to under a sparsity model. If you have an S-sparse system, there is no method that operates at sparsity level or that with number of measurements proportional to S. All of the known algorithms operate under S squared in the generic measurement case, right? So we have this difference that with the generative model, we can exploit the model linearly in its complexity, right? And with a sparsity model, we cannot. So that leads to the question of, well, also like, how does the latent dimensionality of a natural signal class compare to the sparsity level of images in those same class? And there's reasons to believe that under a generative model, you might actually be able to do better than the sparsity level of that particular image, because, well, you're learning a lower dimensional manifold. So if you can learn it, then you should be able to get more efficient representations. So here we have the potential for like a double whammy. One is that the generative models can be optimally exploited, but they can also have lower dimensional representations of the same signal class. So just, I mean, I don't want to spend too much time on it, but just to demonstrate some of the mathematics that are involved in this paper, there's a lot of random concentration arguments. And for example, like this is like the central lemma of the work. It's studying a discontinuous matrix valued random function. So let's say I have a bunch of vectors wi, which are Gaussian, and then now I have two variables x and y, which are this arbitrary points in space. Then I'm going to want to like build this matrix that's like wi transpose added up, but only if wi is aligned with the vector x and y. So now as x and y change, this discontinuously varies, but I want to prove that it's very close to its expectation and actually like uniformly in x and y. So there's a lot of just like technical work that goes into doing concentration estimates like this, and this provides the technical backbone of that paper. So then empirically, this method can work quite well. So these are some results from compressive phase retrieval for handwritten digits. So this row DPR, that's the deep phase retrieval. That's the work that with Leong and Voroninski. And we can see that it can recover approximate images with higher fidelity than methods for sparse phase retrieval in certain parameter regimes. And then we can plot, say, the reconstruction error versus the number of measurements for this deep phase retrieval and compare it to various sparse phase retrieval methods. And what we see is the same sort of thing that was observed for plane compressed sensing by the Bora paper, where at low measurement regimes, you can significantly outperform the sparsity priors. But we notice that in the high measurement regime, like those sparsity-based priors often go to like perfect reconstruction, but the generative modeling priors do not. And so this is one of the challenges that needs to be overcome. But this, after all, we've modeled our signal class as a low dimensional manifold. So if that manifold is not good enough, right, there's going to be some sort of representation error in images that we're going to run our algorithm on. And if our model doesn't describe those images, there's not really anything it can do unless we have some various fixes. Right, so the catch of this, and this is really the visualization of the tail end of that curve that I just showed, is about representation error. Right, so what I'm visualizing here is we trained a generative model on human faces based on this celebrity data set. So this is photos of movie stars and politicians on the red carpet, etc. And then we took this top row of images, which are people not in that data set. And then we said, dear model, please give us the image that's closest to the face that we gave you. And so then we got back what's on the bottom row. And so we can see that in many cases, an approximation of that image was recovered. But there's some like surprising effects that happen. Like this guy in the middle with the glasses and the beard, right? Like his glasses and his beard evaporated, right? The model didn't describe them. Now, if we go, why? Well, many people that are in the celebrity data set aren't wearing glasses and don't have beards. Similarly, like this older woman on the right, a second from the right column, got turned into a younger woman, presumably because the data set is trained on celebrities who skew younger. And so we see that this potential benefit that we're getting from like learning images from data has the potential to actually have significant new challenges, and in particular, the challenge that this is alluding to is a challenge of bias. We have to pay attention to like what's in the training data set, and are we learning biases from that training data set? And when we think about inverse problems, we're often like expressly wanting to image things that were not really in the training data set. Because let's say you're doing medical imaging and there's some new pathology that's never been seen before. You don't want an imaging method to fail because it's new. But if it's new, you don't have training data for it. And so now you see this like conundrum. So I actually want to show, so these generative models, these GANs can have significant representation error. And if we go really far off distribution, maybe it's crazy to try to expect any performance. Remember, this is a model trained on human faces. So let's say we give it we give it this image of a chimpanzee in the fourth column. It rounds that to a human face, which is a woman who's wearing sunglasses that happen to be the same size as the eye socket of that chimpanzee. So you could argue the model's really being successful there. It is finding this closest human to the image that you gave it. And then even all these other images like this butterfly on the right, it sort of tries to turn it into a person. Actually, it looks a little bit like a Van Gogh, but you can see that it really tries to make it a face, right? So this perhaps isn't surprising. Like I said, like we trained a model on human faces. If we don't test it on human faces, we shouldn't expect very much, right? So I want to finish in the last couple of minutes with just like a few quick demonstrations of what can we do to, if we're going to stay with the generative modeling framework, what are examples of things that we can do to get rid of this representation error problem? Like how can we ensure that, say, all images are in the range of our prior? And so the answer is, or one answer is, assume a high dimensional prior. And so so we saw this slide again. Here, you could imagine that the latent space and the data space actually have the same the same dimensionality. So you could even have like an invertible map that goes in between them. And in fact, there's a class of models, normalizing flow models or invertible generative models that have exactly this. And you can do some basic probability. You can have them be a sequence of functions. Each function has a Jacobian. So then the whole distribution, that whole sequence of functions, it's invertible. You can measure the likelihood of any particular image by studying the Jacobian of that composition. This actually allows you to train a model in a way to optimize the likelihood of the data set. And then you can use that model for inversion. And so this is work that I did with Ali Ahmed and this talented undergraduate student, Max Daniels at Northeastern, and also my grad student, Oscar Leong, and Muhammad Asim. And so we showed that using these like invertible priors, we're able to like significantly outperform both sparsity-based priors and these some GAN-based priors at solving compressed sensing. But what was really interesting was like how its performance on out of distribution examples. So these are like the plots from before. This top row are truth images that we're doing compressive sensing on. But these are out of distribution images, right? These are not celebrities, but we train this model using celebrities. So the second column, that's sparsity-based methods using in a wavelet representation. We're operating at enough undersampling that those methods don't work. Right? So then this DC GAN row, that's sort of a generative model a la the central part of this talk. And you can see a lot of the biases that brings in from the training data set, like that guy in the middle's glasses and beards. But this GLOW model, which is a type of normalizing flow, it was also trained only on celebrity data, celebrity face data, yet it doesn't have this problem, right? Or it doesn't have this problem as severely, right? It does give that guy his beard and glasses, and it gives the other guy the turban on the right, and gets the age right of this woman in the second to right column, and even though it was trained on the same data set, right? So then we can ask, well, how far out of distribution can we push this? And so here, this again, we're still doing compressed sensing at a relatively low undersampling ratio, low enough that this conventional methods fail. The chimpanzee, we get correct. Shrek the ogre, there's starting to be a bit of noise. But even if we go all the way to this like butterfly on the right, we get this pixelated image back, but we are still at least qualitatively recovering this butterfly, certainly much better than the wavelet transform is in this case. Right? So this is quite surprising, but like this method, right, was allowing all possible images to be in the range of the prior, and that's very similar to what one would hope, that like you could really be imaging anything. If you had enough measurements, you should be able to recover it. All right, so one last image just to show some of the potential power of this sort of method, and let's just look at the right column here. Right, so this is out of distribution in painting, the out of distribution large hole in painting. Right, so the problem context is I'm going to show you celebrity photos of human faces. Then I'm going to give you this masked image of Shrek. So we're going to block out Shrek's nose. And then the goal is fill in those black pixels. Right? So you can write down a natural formulation given the this normalizing flow model that we described. And you can see in the bottom right, like it gives Shrek a human-shaped nose, but it at least gives Shrek a green nose. Right? And here it learned, right, that faces have noses. It learned about color consistency, but it did not, guess that Shrek's nose would be like a different shape than a human nose. So here, this is quite a successful in-painting output. All right, so just to conclude with some some thoughts, right? So when we think about like generative priors, right, there are a variety of problems for which generative priors may be able to outperform sparsity problems in certain regimes. So particularly in like imaging-based regimes, there's more likely to be in this. This is design. These methods we really study only in the cases of imaging. If you're in other problems which are not imaging-based problems, or maybe very niche imaging problems, this might not be true. For example, if your image is of stars, white pixels on a black sky, then perhaps the sparsity prior really is the mathematically best description of that. And maybe that really should be viewed as this union of subspaces approach. But for more general classes of images, that it's quite possible that generative priors may outperform sparsity priors. So then this can happen for a variety of reasons, a combination of reasons. Right? One is that the actual representations could be tighter. Right? It could use the same number of degrees of freedom, or rather, it can use fewer degrees of freedom to describe the same signal class. And the example for this is, like, if my signal class was a single train going down a single track, right, I need 1 degree of freedom to represent that. If I'm using like a wavelet decomposition, that I'm not going to get away with O of 1 wavelets, right, O of 1 coefficients. So not only could it provide tighter representations, these representations might be able to be optimally exploited in nonlinear cases where like sparsity-based representations might not be able to have that. And so then the trade that this gives us is that a high-dimensional convex optimization problem gets replaced by a low-dimensional non-convex optimization problem. All right, and so then to kind of wrap up that last part of the talk, right? These normalizing flow models, like they can be effective image priors. They can have excellent performance on out-of-distribution images. And what's really surprising about them is that they don't maintain low-dimensional representations explicitly, right? And our normal view about priors and about image compression, et cetera, is that you want low-dimensional representations of data, and that's what gives you your power. But these methods somehow do that implicitly. And that's a lot of the challenge of these neural network-based methods, is so much of it is implicit behavior that we don't really understand. That's why we need further work. But these normalizing flow models do have 0 representation error. So because they are mathematically invertible functions. And so there's like, that's a strength if you can exploit all of the dimensions that are there. So here are just some references for some of the things that I've talked about. This deep compressed sensing area, right, is like the sort of like main initial paper is this Bora paper from ICML. But then I did this work with Vlad Voroninski and Wen Huang for like provable guarantees, provable recovery methods for that. We've looked at a variety of other inverse problems, including denoising, phase retrieval, as I mentioned here, spiked matrix recovery, blind demodulation. There have been some other researchers that have extended or generalized various assumptions. For example, this paper from NeurIPS 2018 talked about convolutional generative models instead of fully connected models. And then Daskalakis and others were able to make better expansivity condition than was proven in our initial work through some very impressive like technical work. So the normalizing flow papers, this ICML paper, and also these reviews, I highly recommend. They're quite nice. And we have, at least for the last 2 years, had a NeurIPS workshop on deep learning and inverse problems. And I encourage you to look at those in the past if you're interested. We also put in for a new workshop this fall or this winter. And so if that gets accepted and you're working in this area, I highly encourage you to submit a contributed poster or talk to that workshop. And with that, I'll thank you for your attention.
Hey, thanks very much, Paul. That was a very interesting talk. There's a question on chat here. I'll just read it to you. Could you talk a little bit more about why normalizing flow priors are working conceptually?
Yeah. So what a normalizing flow prior is, right? So this is a right. So it is distribution learning. What's great about it is that you're able to actually have explicit access to the likelihood of any image. So what that means is that when you train a normalizing flow model, you can find the model that assigns the highest likelihood to the training data set. right? So now what you get in the end, of course, you can train this model for a finite amount of time. You end up getting basically a probability distribution over all possible images. So then if you think of like, what are the images that that model assigns a high likelihood to? Well, that's probably going to be some approximately low dimensional manifold, and it's going to have a tail that's actually, modeled with higher fidelity than you might have with these like GAN-based like low dimensional priors from the middle part of the talk. So really, it's a probability a full distribution over all images that's learned. That means every image has a non-zero likelihood, and that's what really allows it to recover images out of distribution. The cost is you might need to pay a little bit. If you give it more measurements, then you have less of a search space, and it's just maximizing the likelihood over the images that are consistent with those measurements. So in a sense, all it needs to do is to disambiguate between all of the images that agree with your data. And when we think about random Gaussian measurements, like that's a random like linear space that contains a natural point. A lot of those images are going to be random static. And so this model, all it needs to do is distinguish between static and that natural image. So those are some of the ways I think about like, how is that prior working? But of course, I would like, and I sort of have some ongoing research in this area, to be able to extract like from this high dimensional representation what its like best low dimensional approximations are, because they should be there. It's just these models don't make it easy for you to open them up and find what it is.
Interesting. Other questions? Yes, there's another question here. Whoa, that's a long question. It's from Jeremiah. Jeremiah, can I unmute you and you can ask the question? Let's see, where's Jeremiah? Jeremiah's allowed to talk.
Hello, can you hear me?
Yes. Yeah.
Great, awesome. Thank you so much, Paul, for the wonderful talk. I'm curious. So the motivation for using invariable networks, it's very clear. You want to be sure that you can span all of your space. Now, it seems to me that the price to pay when you do that via this normalizing flows is that then the dimension of your representation is basically the same as your ambient space. And so if you do this, I wonder, what can you expect from showing an improvement in terms of recovery? How would this then translate to nice theoretical guarantees? Because before K was much smaller than N, and now N is basically just fixed. So I wonder if you could comment on that.
Yeah, and so yes, that is indeed one of the theoretical challenges that it brings up. So there was a paper recently by I think Eric Price and Alex Demakis and others that actually does provide some theoretical guarantees for compressive sensing under a distributional prior. And the way they looked at it was they said, well, like, consider a covering argument over that distribution, like how many balls does it take to cover like 99% of the probability, and then they can show that you can recover a point, kind of like with a number of measurements given by that complexity, right? So it just the dimensionality of that data might, or the complexity of that data you might measure not by sort of like the linear dimension of a linear space, but by something like a covering number. And so they showed that actually the recoverability using compressed sensing under a distributional prior can be upper and lower bounded by this particular covering. Right. So that's like a really like bringing these sort of giving it like a theoretical footing. Now what that then leads to is, like, you have some natural data now. Well, what's the covering number for for that data as you have learned it. And that, is getting at like, well, what is the structure of real data? And that's always the question we tend to avoid asking.
I see. And then basically the complexity translates, or rather the efficiency of your model then would, supposedly put this, accommodate the covering so that you would get efficiency.
Right.
I see. Thank you very much.
Great. Any other questions? Back to that same issue, Paul. What does it say about how much data do you need to learn these generative model?
Well, yeah. So that, that is a very interesting question, and perhaps much more interesting than it appears, right? So I think to provide perspective on that, I think we need to talk for a little bit about models, about neural network-based models that don't require any training data. Right, so there are models out there, sort of originally inspired by the deep image prior, and followed up in some work that I did with Reinhard Heckel, where we use a random neural network, and with no training data, use it for inverse problems. Right, and so here, like, there's no learning, right, because there is no data, right? Like, learning is about getting better with subsequent data. You don't give me any data, I don't have a learning problem. And so it's perhaps surprising that these like untrained neural networks can actually do very well at inverse problems. And so when we think about how much data is required, we then need to bring that class of models in. And so then, so comments are, at least in this ICML paper, this Asim et al. Paper, where we looked at these normalizing flow models, if you were in distribution, then that learned model would beat, say, the deep decoder. If you were far out of distribution, right, the learned model performance gets worse because it learned the distribution, but the deep decoder doesn't care about the distribution, so its performance roughly stays constant. And so depending on whether at test time you're going to be operating far out of distribution with regularity or quite in distribution might affect which of these methods you would choose. And so it's actually a quite complicated comment, and of course somewhere in between then there's going to be the two methods are going to like intersect and have comparable performance. So we have some plots in this ICML paper that explicitly compare it to deep decoder.
Interesting. Okay, I think we're past 5 minutes past the hour, and so I just want to thank you again for a great talk. The talk will be posted in SIAM's YouTube channel, I think in the next couple of days. Thanks again.
All right, thank you.
Bye.